Where we're going to start is, why am I here? If dental implants were perfect, would they need me? No. They're perfect, but they're not. So if there's risks, then there's a shortcoming, isn't there? So basically we looked at the risks, and they name them quite explicitly. Invading the blood vessels, invading the nerves, doing this, breaking the bone, all kinds of sensitivities, infection. That's on the FDA site. Then for more evidence, there's a lot of literature that says failed implants. One newspaper reported there was 300 failures last year, or 3,000, sorry. And another one said that that's low. There was more than that. So now we know there's a need, right? We know there's a need for implantology. So what we did, we fabricated a prototype. And then we put that prototype through the tests. And the first test we did was in Newark, New Jersey. And they did an engineering test. And that's perfect, because they took a conventional implant and they torqued it like that. And they took ours, of course ours has got roots, and they torqued it. And they came back with, as soon as they put micro torque on that, it leaked. Micro torque, micro leakage, right? Ours couldn't make it leak. And this one surprised me. This movement is called luxation. This is 61% better in resistant luxation. And we take away a third less bone. So it's biomechanically superior to resist torque. So when you're chewing, there's torque forces, we're better. Luxation, we're better. And we take away a third less substratum. So that proved to me that it's biomechanically, biophysically superior. Okay? So now we have to put it to the test. So what did we do then? We got money from the Canadian government. We put them in rabbits. McMaster University, the girl's name is Catherine Granfield. They put them in 12 rabbits. Killed the rabbits 3 weeks, which is sad, 6 weeks, 9 weeks, and 12 weeks. And they made histological slides of what happened. They found at the end of 12 weeks, when they sacrificed the rabbits, where they put the implants in with a wrench, there was cracks, debris, fissures, and they hadn't even started healing. And ours started healing almost immediately. Why? Well, because this one they put in with a wrench. They start off with a hole that big, and then they wrench it in. And when they get to this side, they've killed all the cells. They squashed them, cut off the blood supply. They squashed the osteoblasts, the osteocytes, right? And so basically when we make our hole, it's exactly the right size so that when we put it in there, we can't move it because it's biomechanically locked. But the bone metal interface is passive. We don't hurt anything. We don't hurt those cells, okay? So now we come down to, how do we do that? I say it's, how do we put this thing in there so it's done perfectly and it's not that difficult? And how do we manufacture it so it doesn't cost a fortune? So the first thing we did was we made it with 5-axis machines. This implant with the roots, we had to mill it and whatnot. And then we were very lucky. What came along? Laser sintering. Do you know anything about additive manufacturing? Additive manufacturing is a process where a computer tells it where to lay the implants down, right? So the additive manufacturing made the manufacturing of these implants very, very simple. So that was the next step, laser sintering. The next step is how hard it was to put in. So what we did was we devised a system whereby everything is guided. You put a drill in the sleeve and you bottom it out. And you make the perfect hole every time. You can't screw up. Like you guys could put them in right now. You could put in a dental implant because the lab technician is trained to make that stint the perfect one, the perfect dimension and perfect area, so it goes in the right place, on the right angle, the right size, all the time. So you guys would take a drill and go, boop, all the way down, perfect. Take that out, put a different stint, boop, all the way down. So then we got one that it's biomechanically in the right place, biophysically in the right place, to be able to withstand the forces of occlusion. So we proved that it's biomechanically, biophysically superior, and we proved it's easy to place. So then the next thing we got to do now is that's what we're here right now, is we're going to put them in people. So we get feedback. We'll get feedback from the dentist that places them. We'll get feedback from the people that receive them. How was it? How was the operation? Did you have any problems? Can you chew? And this is a big problem too. You wouldn't know this, but 85% of your failures of implantology is because they're hard to clean. Modern implants are very difficult to clean. And because the pockets, the periodontal pockets are so deep. Okay? So with ours, it's always going to be about 3 millimeters deep, and that's about it. So basically, when it comes to cleaning them, you clean them just like you would clean a normal tooth. So basically, the way we do it, I'll show you. We developed a tray that depresses the tissue away. So what we do in the beginning, the dentist takes impressions and sends them off to the lab technician. And he takes quadrant impressions to be able to, we want to reproduce the entire substratum, right? The entire, so he'll take an impression here, an overall, and an opposing model. And he pours them up. So he takes the model, the stone model, out of the quadrants and puts them in the master and pours up the balance. Okay? So now he's got the perfect model to be able to design the template. Now the rules are pretty straightforward. You can't have an implant any more than 2.5 millimeters from another tooth or another implant. And it's a good idea to have it going in a straight line between the middle of the substratum to the point where you're going to bite, the occlusion. Okay, it's got to be in a straight line. And the other thing is you want it the proper size, because the hard bone is on the outside and the mush is on the inside. So the lab technician will actually measure the size of the model and construct an implant and choose an implant the proper size. So what he'll do, he'll take the model and we got a tooth here, he'll go 2.5 millimeters and put a blue dot. Then you decide to put a 5.2 millimeter implant in there, he'll go by 2.6 and make a red line. And then he goes another 2.6 and makes a blue dot again. Now he can't be any closer than that, so he makes another blue dot over here. And he measures again. And say we're going to put another one in there. So he goes 2.6 and makes a red line. 2.6 puts a blue dot. So now we're going to put implant here, implant here, implant here. So what he does, he takes a saw and he saws on that red line all the way down, right? All the way down to where the bottom of the implant is going to be. And he puts in what I call the target T. It's a little T, it goes in that slit, and you can move it up and down like that until the vertical bar points at the opposing cusp. Follow it? So basically, then he cements that in there, and he puts a sleeve on there to be able to orient the sleeve to where we want to go. You follow that? So basically now he'll put all those sleeves together, and he'll send them to the dentist to be able to check it, make sure it's proper. So when he checks it, he'll double check what the lab technician does. Yes, it's in the right place. Yes, it's the right size. Yes, it's on the right angle, and he'll sign it off. So when the guide sleeve goes to the dentist, that guides the entire process. The surgery is simple. What if this thing moves around, the template? So I would like to have a template that's like this, but it has wings. I call them stabilizing wings. So it can't move. Yeah. So that when we come to drill the holes, we don't have to worry. So the first one we're going to drill is like that, right? It's going to be about 1.5 millimeters in diameter, the drill. And it's going to go down 7 millimeters, right? Then we're going to take out that sleeve, which is 2.75. Then we're going to go down there with our second drill. Now this drill is different. This drill only cuts on the outside. The center of that drill is blunt. The 1.5 millimeters at the bottom of that drill doesn't cut. It just goes down and hits and stops. So then he goes down and he widens the hole. right? Now this is the next sleeve that I believe is very important because I've done it a lot of times. There's a thing that we're going to have is going to call the guided trephine. You guys know what a trephine burr is? Okay. So this guided trephine, we take everything out of there, and this trephine goes in and makes a beautiful cut right in here, just like it was a cut with a razor blade, so that the tissues are not maimed. They're pure. They're perfectly cut every time. So now we've got a cut the size of our implant, and we've got a 2.75 millimeter channel so far, right? So all we do now is we just widen it to the size of the implant, which is going to be the size of the sleeve, 5.2 millimeters, right? That's going to be our circumference. So now we've got a hole 5.2 millimeters in there and 7 millimeters deep. Now we got to drill our roots. But here's what it looks like. There's our drill jig. The handle goes out here. So put that in there, and there's a channel. The drill goes in that channel and cuts at 12 o'clock. And when he bottoms it out, it's exactly 6 millimeters, right? He leaves that in there, stabilizes the drill jig, and he makes this other one. So he takes this out, he takes this out, he takes this out, and he puts the implant in. Simple as that. And it really takes the skill factor out of implantology, so that anybody can do it.